So now we come to the chemical properties and chemical properties of glucose. So we're going to be discussing the chemical properties of D-glucose. Now, if we carefully read the structure of glucose, we have learned that on the top we had the aldehyde group. So we had the CHO group. Then on the second carbon, the OH was on the left, and on the rest of them, the OH was on the right. This is how we remembered the structure, and it was accompanied by H at the chiral carbons. Okay, so this was the structure of glucose that we had learnt about. Now, what this glucose does is when we place this glucose in a basic medium. So, what is a basic medium? It is the presence of OH negative ions in the medium. So, when this glucose is placed in a basic medium, it tautomerizes. So, what are we going to learn? That when it is placed in a basic medium meaning a medium containing OH negative ions, glucose is gonna tautomerize. Okay, so glucose is gonna tautomerize. Now, what does this tautomerize mean is that if we start naming, suppose we name this O as 1, this C as 2, and this one as the third one. So we have got this atom is the first one, this atom is second one, and this particular has a third one. We're going to be switching the positions of the double bond. How we're going to do that is that in the next structure, when it is placed in a basic medium, what happens is this double bond now comes in between the second and the third carbon. So if we see what is happening, now we're going to place our double bond between the second and the third carbon. Okay, so the second and the third carbon are going to be here, and we're going to place a double bond between them. Okay, so now if we look carefully, this particular carbon and this, okay, so we have placed a double bond between these two, and this one is the double bond that we're talking about. Now, if we carefully see and place the other groups that are left, what is actually going to happen in this tautomerization is that this H, which was at the third position, the third carbon attached to it, now it is going to be going towards this O, and now we're going to be getting an OH. So, what are we talking about? We are saying that this H is going to go with this O, and so now we go be getting an OH over here. There was an H already present, and in this particular, this third place over here, what is going to happen is an OH remains, and the H on the left side is already lost to this O. So what is happening in tautomerization basically is that an H is moving and a double bond is moving, okay? And the rest of the structure looks exactly the same. So H, OH, OH, and we have got a CH2OH, H, H, and OH. So now we have tautomerized the structure, and we place the double bond that was between the first and the second, between the second and the third. Okay, the double bond is shifting. Now, this particular structure that we have just drawn, this one, is going to be very helpful. And how is going to be that? So, when I draw this particular structure here, see, this is the D-glucose that we had originally, and now it has tautomerized. This double bond is now shifted to the second and third position. Now what is going to happen is that we're going to shift it a little more. So now what we're going to do is we're going to place this double bond between the first and the second position. Okay. So now we're going to be placing the double bond here. When we do this, what particular structure do we get? We get a C and a double bond O. This H, which was with O, cannot be with O now, since the valency of oxygen is satisfied. So this H moves to the top and accompanies this CH2, and we have an OH. So we originally had an OH and an H group, and now we have another H. So it becomes CH2OH. So what is happening here is the double bond is shifting between the first and the second. The rest of the structure look exactly the same. So we have something like this. Now, if you notice the structure very, very carefully, you can clearly see that this structure is the one we talked about. And where? We talked about it in fructose, because this structure is nothing but D-fructose. See, a CH2OH at the top, accompanied by a C double bond O, that is a ketone group, and then we have a CH2OH at the bottom, and H on the left, and the rest of the carbons, and the H on the right on the first one. So what we notice is that this particular structure is nothing but our D-fructose. So we just clearly see that this is nothing but the fructose. Okay, now moving on, this particular structure that we started with, so this particular second open structure is going to be helping us in discovering, in finding out a new compound too. How is that? If what we do now is that this double bond, we're going to shift it back to this O, that is what we originally had in D-glucose. So this double bond, this particular double bond is going to be coming back to this position, and this H that was present at OH, so this H will come back to its second carbon over here. But now this H, instead of coming to its original position, which was on the left hand side, now can be shifted because we are shifting the bonds. And now this H in the next structure that we're going to be drawing, the new compound that we're going to be forming, this H is going to be coming on the right. So what are we talking about? Now the situation will look something like this. I will have a C here, and what we're going to be trying to do is that we're going to be placing a double bond here between. This is very similar to the case which we had in D-glucose, but only there is one little difference that we notice is that in this particular carbon over here, what are we going to do? We're going to just place the H on the right and the OH on the left, and the rest of the structure look exactly the same. So now also there is one configuration, or the configuration of only one carbon is differing in this particular structure from what is present in the D-glucose. And now this compound that we just formed is named as D-mannose. D-mannose. Okay. So this, we got a D-mannose, we got a D-fructose, all because we tautomerize this particular glucose in an acidic medium. Okay. So all of them will be existing in equilibrium. Say if I have D-glucose in a solution, then all the rest of these, that is the D-fructose and D-mannose, will also be existing in that solution. Now, we notice that in D-mannose and D-glucose, there is only a configuration difference at the first chiral carbon. And we have already studied that if only one chiral carbon differs, then we call it an epimer. So now these two, apart from being isomers, they're also epimers of each other. Okay. So D-glucose and D-fructose are all tautomers of each other. So this D-glucose and D-fructose are tautomers of each other, and D-mannose and D-glucose are also tautomers of each other, and they're also epimers of each other because they're only differing at the positioning of this C1, this C1, only differing at the placement of OH on the left and the right respectively. So we can now just write and put a totaling factor, what we learned right now is that D-glucose and D-mannose are epimers. They're only differing at the placement of OH at the C1, so they are epimers. Also, because they all are they're isomers too, please note that. But the main factor that we learned here was that D-glucose, D-fructose, and D-mannose are tautomers. That is the main point of highlight of all this. So they are tautomers. Okay, so this was the main point. Now, if we notice that in D-glucose, we learned that D-glucose shows Tollens reagent and Felling's reagent test. So it gives both the test positive, and we also call D-glucose a reducing sugar back then. So now, since D-glucose, if I put it in solution, it also is getting changed to D-fructose and D-mannose. So now our D-fructose and D-mannose will also show Tollens and Fehling solution test. Please note that these both tests are actually giving positive tests towards aldehydes. But now what we notice back here is that D-fructose is actually not an aldehyde, it is a ketone. The rest of them, D-mannose and D-glucose, are aldehydes, so they are gonna be giving positive tests towards Tollens and Felling's reagent. But our D-fructose is a ketone group, and we know that ketone don't give Tollens and Felling's test. But since it is in equilibrium in the mixture where D-glucose is present, so therefore, D-fructose is also be going to showing our Tollens reagent test and the Fehling solution test. Okay. So what are we going to write here is that all of them are, so if you put them in a category, they are all reducing sugars. That is, they will give, which test are we talking about here? The Tollens reagent test and Fehling solution test. Okay, so they are all reducing and they're giving tolerance reagent as well as the Fehling solution test. Now, please keep that in mind that although these two tests are given only by aldehyde group, but our deep fructose over here, which is actually a ketonic group, it has actually a ketone group present, will also be showing this particular test. So, D fructose, just writing reminder here that we have to remember is that D fructose, although having D fructose, although having a ketone group, will give positive test for both of them. Okay, will give a positive test for both Tollens and Fehling, for both Tollens reagent and Fehling solution. This was the point of highlight that we wanted to see about these three tautomers which are formed when D-glucose tautomerizes in a basic medium. Please note that this only occurs when it is in basic medium, and all of them will be existing in that solution because all of them are tautomers of each other. In if one group is showing a particular test, the rest of them will follow suit with them and will show the particular test too. So this was the tautomers.